Why is it that games programmers talk about all these different types of spaces? Everybody seems to talk about model space, world space, and view or ice space, all as being different spaces, but is that actually true? And it gets even worse because we've then got clip space, NDC space, and screen space. So that means we've got 6 different types of space, but what if the word space is being abused? Let's start by considering if there's any difference between model space and world space. World space refers to the entire universe, not just planet Earth, so literally all of 3D spatial existence, which includes galaxies, stars, spaceships, planets, animals, buildings, people, and everything else that you know exists. Let's say you decide to use a skybox cube as your world environment, in which case you could set the depth testing to allow the skybox to obscure the models during rendering, which is what you can see happening here. When the building is scaled very small and our viewpoint is at the centre of the cube, we have a perfect view of the scene and a tiny building sitting on the floor beside us. If we then drastically increase the size of the building to become the size of the entire visible universe, which in this case is just the skybox, model space and world space now refer to the same volume of space, and so other than the amount of space occupied, model space and world space are exactly the same thing. So we should really just be thinking in terms of 3D space, and therefore any models within 3D space can either be transformed as individual collections of points by individual transformation matrices, or we can transform all the models by just a single matrix. So for example, we can see the opposite side of all 3 cars, or we can also apply individual transformations, or not transformed at all, which looks like this. So that's model space and world space, but is view space also nothing more than just 3D space? If we want to see this plane from the point of view of this camera, do we move and rotate the plane like this? Or do we somehow move our virtual heads to be at the position of the camera like this? Which is what we would do in real life if we wanted to take a photo. The solution is to do the only thing that we can do, which is to transform the model's vertex positions in 3D space, thereby creating the illusion that we're looking through a camera that is positioned somewhere within the scene. For example, all 3 cars are now being moved and rotated independently of one another whilst the camera viewpoint remains the same, but then to make it seem as if the camera view is being rotated, it's actually the entire scene that becomes rotated, which from the point of view of the view frustum's origin, which is the camera, the near plane looks like this. And so the conclusion is that view space, just like model space and world space, is literally nothing more than just 3D space. Just so we can appreciate how those 3 spaces are actually all just the same one and only 3D space, let's take a look inside the Vertex shader to see how we apply the transformations in there. So this is some of the GLS shader code that I'm using to control a model helicopter. For each cycle of the main loop on the CPU side, the entire model is rendered by making just a single draw call. The same initial vertex position values as exported from the 3D modelling software are fed into the Vertex shader for each draw call. The helicopter consists of many different meshes, and so I'm using the mesh number input attribute to select the correct transformation matrix for the mesh vertices currently being processed. This is the GL position output value for the vertex currently being processed, and then other than the projection matrix, which we'll consider in just a moment, we can see that each individual mesh has its own unique transformation applied to it, but there's only one view matrix, which makes sense because as we've just seen, we want it to transform the entire scene. So that's model space, world space and view space, which are all just 3D space as we've just seen, but we also need to understand clip space, normalised device coordinates, NDC space, and screen space, which brings us to the projection matrix. Now the purpose of the projection matrix is to project the x and y position values of points in 3D space onto the near plane of the view frustum, which is just a 2D flat surface like a photograph. Keep in mind that I haven't labelled the far plane in the illustration, which is simply so that we can imagine the far plane to be as far away as required to capture the scene. This is what the model plane looks like from the camera's point of view as projected onto the near plane when the model is at this position and orientation in 3D space, and then if we rotate the model in 3D space we can see how it compares to the image on the near plane. Calculating the x and y projection is well easy. For any point in 3D space we just need to divide its y value by its z value, which gives us the slope of the hypotenuse, and then we multiply that ratio by the distance between the camera and the near plane, and that's it. And for the x-axis it's exactly the same logic. But if that's how easy it is to get from ordinary 3D space to 2D screen space, then you might well be thinking, what the fuck is clip space and what the hell is NDC space? Of course, clip space and NDC space both have X, Y and Z coordinates, which does indeed make them 3D coordinate systems, but neither clip space nor NDC space are anything like ordinary 3D space. So let's start with normalised device coordinate space, which we call NDC space. How does the view frustum become an NDC cube that has a size of -1 to +1, as is the case for OpenGL? The first thing to notice is that as you're looking directly forwards at the near plane, it corresponds to looking along the field of view projection lines of the view frustum through 3D space, which also applies to the NDC cube as you're about to see. The resulting X and Y projected values of the near plane are scaled to the range -1 to +1, which means they now represent the front face of the NDC cube. The Z values, which are also scaled to the range -1 to +1, but along the Z axis into screen, are used for depth testing which point to display when two or more points project onto the same position of the near plane, and so it's only because we associate the depth values with the fundamentally separate results of XY projection that we end up with a cube. When we're looking at the view frustum, we're looking at 3D space, and so the true size of each Spider-Man is as he appears within the frustum, but in NDC space they all appear to be the same size. Also notice that if I'd managed to animate the Spider-Men more precisely, then when looking into the cube, we'd actually see the underside of their chins instead of seeing them straight on, and so as the field of view increases, so does the perspective distortion. But all of what we've just seen is only accurate if the near plane is square and if we don't bother to scale the depth values to the range -1 to +1. For example, if a widescreen near plane is scaled to become square, we can see how the Spider-Men become thin horizontally, and because the depth values are scaled non-linearly to NDC space, so that more depth values are being used to represent models closer to the screen, which then gives us better precision closer to the screen, we can see how the Spider-Men become spread out along the Z-axis. Now, unlike the perspective distortion caused by the field of view, which exists as part of the final image, the distortion caused by scaling a rectangular near plane to the front face of the NDC cube becomes undone when it's mapped back to the viewport size. And the distortion along the Z-axis isn't actually visible because we only get to see the near plane, which is what you can see happening here as the 2D rendered image of our 3D Spider-Man is being rotated. In conclusion then, 3D space and NDC space both have perpendicular X, Y and Z axes, but NDC space is definitely not the same thing as ordinary 3D space. And so to some extent it actually makes sense to think of the NDC cube as being a 3D photograph simply because its Z axis is an extension which runs directly along the projection lines of the 2D image. And finally we've got clip space, which is also definitely not 3D space. It's simply the 3D to 2D projection that we've already looked at, but with the divide by Z part of the calculation being performed as perspective division after the clipping process. And for anyone interested in understanding why clip space actually makes any sense, there's a link in the description to another one of my videos which explains it in more detail.